is the composition of this operator and the operator of multiplication by G. Okay, so it's multiplication by G. Then psi q g of x to the power u equals this operator tq applied to multiplication by g, so the sum of over all multi-indices gw, the coefficient of g, times x to the power w plus u. Okay, and this is equal to the sum over all v multi-indices of g q v minus u times x to the u. Also, we set gq of x is g of x to the power q, meaning just term-wise taking powers. So it's the sum of over all multi-indices of gw x to qw. Okay, and in this notation, the composition G and TQ is the composition TQ times GQ. And this is the same as psi Q GQ. Okay, we'll need this commutation relation. Pardon me? Pardon me? Yes, Q is p to some power. Maybe we'll later on need p to the power r. Certain power of p, yes. Okay. So one more notation. The absolute value of u is just the sum of its coordinates. Okay. And a subring R naught in R of a convergent series. So more precisely, R naught is the set of all formal power series GW x to the power W such that there exists certain positive constant m such that the p order of the coefficient GW is at least m times the sum of coefficients of W for any W multi-index. So this subring is closed under the operation G goes to GQ. GQ is a substitution of Q's powers of our variables. And any series in R naught converges in a certain polydisk. D of r to the power n for certain radius bigger than 1 because of this condition. Okay, so for example, this theta series we discussed of a times x to the power w, I mean, theta was a function in one variable. Yes, so we substitute this one variable, and then it lies in R naught for any a in the unit disk and any multi-index. Just because we had this convergence, at the very top. Okay. Now we'll need the following lemma. So let G be a convergent power series, and psi is a psi GQ, this endomorphism as above. Then the trace of this endomorphism psi to the power s is well defined for any positive integer s, and it is equal to the sum over roots of unity, x q to the power s minus 1 equals 1, of g of x, g of x to the power q, and so on, up to g of x to the power q to s minus 1. Okay, so let's prove this. Pardon me? Yes. So we want to. So in fact, the actual terms in the expansion of theta, of this theta, will be only multiples of w, right? But those multiples of w will have coefficients that grow in an appropriate way just because we know the convergence of theta. So it is greater than 1, so yes, there is a convergence of theta is bigger than 1, and so we're in good shape. Yes. Pardon me? N variables. It means that I just take all the variables of this multivariable to their powers. So all the coordinates are these roots of unity. Okay. So proof is first s equals 1. And then psi of x to the power u is the sum over all multi-indices v of G QV minus, sorry, QV minus U, x to the power V, and hence the trace of psi is equal to the sum over all multi-indices U, G Q minus 1 times U. Okay. I mean, trace formally just as the sum of all diagonal elements in the evident basis of monomials. And then we have to check that this sum actually converges. And this means that the trace is well defined. And then we have to actually compute it. Okay. Well, just by our assumption, it does converge. Now, just by the standard theory of abelian group characters, for all the indices I, the sum over roots of unity xi to the power q minus 1 xi, the roots of unity, the sum over these roots of unity, their wi powers, it is equal either to q minus 1 if wi is divisible by q minus 1, or just 0. Okay. And this means that the sum over all roots of unity. Yes. What is this? Well, this is some basic relation from the high school, that if you add all the roots of unity, then you get 0. No, I mean, this I is just an index. It doesn't matter anything at all. So here I just have one variable. And I add over the roots of unity of this degree, I add their powers. So if these powers are all 1, you get q minus 1. That's evident. If they're not all 1, then I get 0. That's also evident, isn't it? No, this is evident just by definition of G. We know that G was in R naught. So this series will converge. Okay. We're trying to compute it. It converges just because our function G naught is convergent. We are trying to compute it. Right? So the sum over all multi roots of unity, x to the power w, will be q minus 1 to the power n if w is divisible by q minus 1, meaning that any coordinate of w is divisible by q minus 1. And 0 otherwise. Okay. And so the sum of over roots of unity of g of x will be equal to the sum over multi-indices gw times the sum over roots of unity, multi-roots of unity, x to the power w, and it will be equal to q minus 1 to the power n, the sum over multi-indices u, g q minus 1 times u, and will be equal to q minus 1 to the power n, the desired trace. Okay, so we proved our statement for s equals 1. All right? The only thing is that I wrote something stupid, q to the s minus 1 here. Sorry, not in the power, but well, not in the topmost power, but in the middle power. Sorry. Okay. So now we want arbitrary s. So this was s equals 1. So s bigger than 1. Then psi to the power s, by definition, psi was this psi gq, and psi gq was this composition. So I have to compose, well, 2s things like this. And then we will use this commutational relation to pass all t to the left. So it is t q composition with g, then composition of tq with g again, and so on. Well, let me write psi to the power s minus 2. And let me try to take all t to the left. So it will be tq, composition tq, composition gq, composition g, composition psi to s minus 2. And then this is tq squared, composition g, composition gq, composition psi to s minus 2. Oh yes, because they are just multiplications by certain function. Multiplications by any functions commute. So where are we? It's g times gq times s minus 2. And then I extract more t and g from this psi to the s minus 2. So I get tq squared times tq times g composed with gq, q, g composed with g, composed with psi to s minus 3. And then I will get tq cubed, composed with g, composed with gq, composed with gq squared, composed with psi s minus 3, and so on. There is some pattern, if you see. So in the end, I will get tq to the s, g, gq, gq squared, and so on, up to g to q s minus 1, and this will be psi q to the s, g composed with gq, composed with so on, with gq s minus 1. Okay, so now we can change variables, so to say. Substitute q by q to the s and g. By this composition, g, gq, gq to the s minus 1, and apply the previous result. Okay, so the lemma is proved. Yes? But we already proved this for one. We proved this for psi itself. And now we obtain just this. It's psi, but for some different function and for some different q. It didn't matter which q we had. Okay? Pardon me? This? This? And what was the question? I took one more part of this s minus 2. So I just took t q times g extracted from here. And then I, yes. Mm-hmm. Okay, so this lemma is proved, and now we consider the matrix A over the endomorphism psi, which is TQ composition with G over our ring R naught. And again, I take the same basis or topological basis just of monomials of this ring. So you see the basis of R naught is the same as the basis of R. It's not quite really the basis, it's topological basis, like in Hilbert space, for example. So I take the same monomial basis and compute everything in this basis. Matrix elements, traces, and now I will need the characteristic polynomial. Yes?
The same for any choice of such basis.
Well, if the trace is well defined, then it will. I mean, if it converges, absolutely. So then it will be the same in another basis. Yes. Like in the Hilbert space, for example. So we take this matrix and compute its characteristic polynomial. Namely, determinant of 1 minus a times formal variable t. And this will be, again, certain formal sum. But we will see shortly that it converges. So the coefficients are just the sums of principal minors. M by M minors. So we estimate the p orders of the summons of these minors. As follows. So we'll have some m tuple of positive integers, and its permutation. So another m tuple of positive integers, and the corresponding summand will have the order g q sigma over u1 minus u1 times g q sigma of of u2 minus u2 times so on times g q sigma of um minus um. So u is well, u1, so on m is an arbitrary m tuple of integers, right? And sigma from n to n permutation. Or maybe, what should I say? Maybe not that ambitious. Maybe just this. Ага. Okay. Pardon me? The entries of our matrix A. They're coefficients of the G power series. U sigma m. Pardon me? Yes. So didn't we compute it here? Just on this blackboard. Okay. And then by definition of this subring are not convergent subring, then this order is this order is at least capital M. Where do I have? Yeah, here it is. This capital M times but maybe I did confuse you. Sorry. So Yeah, I'm sorry. Uh, so these guys are, well, each of them is a multi-index, right? And they're M tuple of multi-indices. And maybe then I should really.
But we still permute the multi-indices.
The multi-indices, yes.
Not their, you cannot do sigma to the multi-index because sigma acts on 1 to m numbers, just numbers, right?
Yes.
So what's written right now is correct.
Okay. Okay. Thank you. And so what do I write here? I write here Q U sigma 1 minus U1 plus so on plus Q U sigma M minus UM. Okay? And this is M times sum of Q U sigma whatever I minus sum of UI. Okay. Here? No, here. This thing is just the sum of all coordinates. Where we had it? This notation. Here it is. Just the sum of all coordinates of an n-tuple of positive integers. So it's the equality, and moreover, it is equal to m times q minus 1, the sum of ui. Okay. And hence, the order, p order of these coefficients of the characteristic polynomial tends to infinity as m goes to infinity. So the power series converges in the unit disk. This formal series converges in the unit disk, but in fact it converges everywhere at all. So 1 over m, the p order of Bm, also goes to infinity as m goes to infinity. Since there are but finitely many n-tuples U with a fixed absolute value, and what shall I raise? Just one moment. No. Okay, let me erase this, but maybe you will remember what is our convergent subring and this lemma. We will eventually need it. and then I will refer to the erased lemma, vanishing lemma. Okay, so there are finitely many such, and the mean value over the absolute value of u over a finite set over u, that is 1 over m, the sum over ui, absolute values, tends to infinity as m goes to infinity. So not only the sum goes to infinity, but 1 over m also does go to infinity. And so this order tends to infinity. In other words, this power series, the sum over what is it? Bm t to the m, converges in the whole Tate field. Okay. And then you will have the home assignment exercise that, as well as in the finite dimensional case, since everything converges, the determinant of 1 minus at will be equal to the exponent of a negative sum of a trace of powers okay. So we discussed this a couple of weeks ago in the finite dimensional case with allusions to K groups and something like this. But anyway, it's something very well established in the finite dimensional case. But now there is a generalization to the infinite dimensional case under the assumption that everything here converges. So you maybe approximated by finite dimensional trace and determinant determinants. Okay. So now our main goal for today will be the proposition that the zeta function of our hypersurface, well, so by definition, it is a formal power series with positive integral coefficients, and well, a fortiori, it lies in the formal power series with coefficients in Tate field. But the proposition claims that it's not only formal, but it is a meromorphic function. That is the ratio of two entire functions. Two entire functions like f. No, f is bad. Maybe f capital F over capital G. So, so they are formal series, but they converge everywhere. That's the meaning of the word entire function. Okay, and this is the key point. Then from this purely formally, you deduce that they must be polynomials. If you know this strong convergence property, then just by some linear algebra or combinatorics, I don't know, next time we will deduce that they're polynomials. So the key point is just this. You need this meromorphic statement. Okay, so let's start the proof. And it'll be by induction. In N, surprisingly. So N was the dimension of our hypersurface plus 1. So assume we already know for all smaller values. So if no then it suffices to prove for some modification of the zeta function z prime. Namely, the zeta function proper counted points in the affine space satisfying this equality, f equals 0. And we're going to count the points in the punctured, in the torus. Like this. And it's very similar to your home assignment problem, where you had to deduce the rationality for rational given rationality for affine hypersurfaces, you needed to deduce it for projective hypersurfaces, for example, or arbitrary projective varieties. So this z prime is by definition the exponent of, pardon me, yes? For certain modified zeta function, which I'm just introducing.
Yes. And what is h sub f prime?
It is the intersection the set of x in an such that f of x is 0 and xi never vanishes. So we intersect with this torus inside the affine space. Okay. So we again take this exponential counting function and prime. R is the set of, just as I said, of x1 and so on, xn in fq to the power r, but now not fq, but without 0 to the power n, such that f of x is 0. And well, equivalently, this condition can be stated as x to the power q to r minus 1 will be 1. And this will make contact with what we counted before. So well, maybe it was there. Yeah, we counted such sums before. So we'll eventually reduce this to the trace computation as we had. Okay. Yes, yes. Well, okay, let me try to use this. So just a technical modification to make contact with what we just computed. What I'm just erasing. Okay. So we have z over hf and t equals z prime of hf and t times the discrepancy. The discrepancy is the sum of nr minus nr prime times t to the r over r, exponential of this. And the second factor is the zeta function of the union of hi and t, and hi equals just the hyper surfaces. So it's f equals 0 and xi equals 0. Right? We assume that no coordinate vanishes, but otherwise some coordinate does vanish, and we get this. Okay, so this is a hypersurface of dimension n-2, for which we already know by our induction assumption what we want. Okay, and this equals the product of z of hi t by the inclusion-exclusion formula. Divide by the product over I less than j, zeta function of hi intersected with hj t, and multiple, well, maybe I should say times this product inverse, but then times I less than j less than k, z over hi intersected hj intersected hk, and t, and times so on. But any factor, as I said, is of smaller and smaller dimension, and we, by induction assumption, know what we want about them. Okay, so we reduced our problem to this zeta prime. Okay, so fix some s and let our q be p to the r, and we'll have a number a in the finite field q to the s. Then the last time we argued, I recalled at the very top that epsilon to the trace of a is equal to theta of the Teichmuller representative theta of a, theta of Teichmuller representative to the power p times so on, times theta of Teichmuller representative to the power p to the s minus 1. Okay. And now let's consider such an extended sum. So I add one extra variable. But all my variables are invertible in the multiplicative group of the finite field. And then I take epsilon to the trace of x naught times f over x1, so on, xn. And then it will be equal to q to the power s n s prime minus q to the power s minus 1 to the power n, since we already argued the same way just half an hour ago. Since the sum of over all invertible elements of our finite field of epsilon to trace of x naught times u, or maybe u is a bad variable. What is better? Y is equal to either -1 if y is invertible, and qs minus 1 if y is 0. Okay. Yes. Just because, well, I said a few words in the beginning of last time about this counting function and its Fourier transform. So that's what goes on, but formally, so you introduce this counting variable, extra variable, x naught. But formally, well, either f is equal to 0, and then you count just ones, right? Or else and that's what you get. Or else it's not 0, and then if you summed up over arbitrary x naught, you would get 0, as we argued. But here we suppose that x naught is not 0. So we just dispose of one term in this 0 sum, and this term was 1. So the sum is -1. And you get that many summands. If it vanishes, we get this. If it doesn't vanish, we get that. Right? Because we're summing over all x naught. when f vanishes, this clear, I guess. When it doesn't vanish, we're summing, take this y. The value of f is y. And you are summing this over all non-vanishing x naught, right? And y is not vanishing either. So this sum is -1. Because if you summed over all x naught, all over, including 0, you would get just 0. But you sum the characters, non-trivial characters, over the whole field. But now you subtract the value at 0 because x naught is not 0. You subtract it, you get -1. Pardon me? Why this? Just because we have many variables, and many variables.
So it is a number of sets of variables. If you get 1, it gives a contribution q in degree s. And the second term is given by all y's 0.
Mm-hmm.
So for any set where f doesn't vanish, we get -1.
Mm-hmm.
And we need to sum it over all possible sets where f doesn't vanish.
So, yes. Oh. Yeah. So,
Why we get in the first term q in degree s? So for any x naught, we get n sub s prime.
right. But there are q to the power s possible choices of x naught, right?
But it should be non-zero. So for q in degree s -1. And as you write there,
Yeah. Okay, so you see it's q to the power s -1 times n prime s, right?
yes, and
Minus the total number of those things, which is q to the power s -1 to the power n, minus those guys which contribute to the first term. So minus m prime s, right? well, okay. Do you agree with this?
But x0 can be arbitrary.
Pardon me? S can be arbitrary, but it's fixed.
No,
Who?
x0 can be arbitrary. So for any set.
So once again, when
For any set that contributes in sub S, there is q in degree S minus 1 possible x0s.
no, but we're summing over all x nodes. We're summing over all non-vanishing x nodes. And this sum, as you wisely remark, gives you this minus that. And then it cancels out, and you get. Welcome. But I am forced to erase something. Let me maybe erase this. So we're proving that our zeta function is a ratio of two entire functions, yeah? I'm erasing this, okay? Okay, so now we replace all the coefficients in x0 times f of x1 and so on xn. So this was a polynomial in n+1 variables. And we replace its coefficients by their Teichmuller representatives. And we get capital F of x0, so on, xn, equal to the sum of ai x to the power wi. So this is some polynomial with now Tate field coefficients in x0, x1, and so on, xn. And then from this formula, we get that q to the power s n prime s equals q to the power s minus 1 to the power n plus the sum over x0, x1, and so on, xn in f q to the power s multiplicative group, epsilon to the trace over x0, f of x1, and so on, xn. And this is equal to q to the power s minus 1 to the power n plus by the very top formula, the sum over multi-roots of unity, x to the power q to the s minus 1 equals 1, product over numbers I over all indices I over theta of AI x to the power wi, and then theta of AI to the p x to the power p wi, and so on, and then theta AI to the power p rs minus 1 times x to the power p to the rs minus 1 times wi. Okay, and all the coefficients of our initial polynomial f were lying in fq, and this q was p to the power r. This means that ai to p to the r equals ai. And now set g of x0 and so on xn is the product of theta functions, theta of ai x to wi, then theta over ai to the p x to the p wi, and so on, and then theta ai to the p to r minus 1 x to the p r minus 1 wi. Okay. Then we'll have that q to the power s and s prime equals q to s minus 1 to the power n plus the sum over the roots of multi-roots of unity x to the power q to s minus 1 equals 1, g of x times g of x to the power q times so on times g of x to the power q to s minus 1. Okay, and I'm almost done, but what shall I erase? Let me erase this. Okay. So we know that theta over ai to the power p to any power whatever k x to the power p to the k wi lies in R naught, and hence this G of X naught and so on, Xn. Pardon me? Pardon me?
Она лежит в R0 как функция чего?
Of axis. And hence G of X naught also lies in R naught. Well, in fact, it is now of n plus 1 variables, but that doesn't really matter. And hence, by the erased lemma, vanishing lemma, Qs to ms prime equals Qs minus 1 to power n plus Qs minus 1 to power n plus 1, the trace of psi to the s. And hence ns prime equals the sum from 0 to n of the binomial coefficients q to the power s times n minus I minus 1 plus the sum from 0 to n plus 1, negative 1 to I n plus y binomial, choose I, q to the power s n minus I, trace of psi to the s. Okay. And we set delta of t is this quadristic polynomial that is still upstairs. And this is the exponential of negative sum of traces of psi to the s times ts over s. Okay, and then the desired zeta function modified is the exponential of the sum of n prime s t to the s over s and equals the product of exponentials of the first thing here, sum, from y equals 1 to n, q to the s n minus I minus 1, ts over s, this exponential to the power minus 1 to the power I, and choose I, times the product from I equals 0 to n plus 1, exponential of the sum over s, q to s n minus I, the trace of psi to the s, t to the s over s, to the power minus 1 to I, n plus 1, choose I. Okay, and finally this is equal to the product from 0 to n 1 minus q to the power n minus I minus 1 to the power minus 1 to I plus 1, and choose I times the product from I equals 0 to n plus 1, delta over q to n minus I t to the power minus 1 to I plus 1, n plus 1, choose I. Okay, and now all the factors converge in the entire Tate field by the lemma, which is not. Which is also erased by another lemma. Okay. Okay, so we are done. Yeah, yeah. Mm-hmm. Yeah.
So we need to show that the driver is ratio of two entire functions.
Mm-hmm. And we got quite a few functions, maybe, like 2n plus 2 functions, I don't know. But any of them is entire. Huh? Pardon me?
The first thing is not a function. It doesn't depend on time. Yes.
Ah, right. Yeah, right. This is just constant multiple, but here we have products of 2, n plus 2 functions which are entire. Yeah.
Each function delta is entire.
Mm-hmm.
Why it is entire?
I think we proved it. We proved that it was it was this sum, and it converged everywhere.
Yes.
We proved it. Okay, so the proposition is proved that we got a meromorphic zeta function, and then the next time it will be just purely formal argument that doesn't need essentially anything else.
So the first needs set of functions.
Doesn't need what?
Set of functions that we construct.
Nothing else. We just need to know that this zeta function is meromorphic. And then from this meromorphicity, it will formally follow that it's actually rational. And do you want to submit your home assignment by any chance?
Я, к сожалению, не успела наделать где больше. Я не хочу сдавать частично, я тебе лучше ее
Okay.
побочно. Еще хотела
Submit your home